Hello everybody. In this video, we're going to go over how to compute the probability values associated with specific probability distributions using R. So I've also done another video series where I show you how to do these calculations in Excel. Some of the explanations behind certain problems are much more detailed in the Excel videos. So I encourage you to watch those videos also. So let's begin. So we're going to learn how to compute probabilities for three different distributions: a binomial, Poisson, and normal distribution. So first, let me just set up the basics. So I'm setting up my working directory. So that's all set. Okay. So R does things a little bit differently compared to Excel. And we're going to learn about three important types of functions which we'll use to do the next few calculations. So there are four different functions related to probability distributions in R, or essentially, there are four different prefixes followed by the name of the distribution. And each of these prefixes has a different functionality. So the four prefixes are the letters D, P, Q, and R. So we are not going to look at the fourth one right now. We won't use the prefix R in this course. So we'll learn about the first three. The prefix D, followed by the name of the distribution, say D binom, D Poisson, D Poise, or D norm, gives us the density of the curve at that particular point. So when we're able to, this is nothing but computing the probability of a specific value. And when we're able to compute probability of a specific value, we are particularly speaking about discrete random variables here. So we are essentially talking of the PMF, or in other words, the probability that the random variable equals some specific value X. So this prefix D is more applicable for discrete random variables. The second prefix is the prefix P. P followed by the name of the distribution actually gives us the cumulative probability. Or in other words, the probability of a random variable lesser than or equal to some specific number. And this functionality, remember the CDF, cumulative density function, can be defined for both discrete and continuous variables. And the same applies to this prefix also. The other prefix, the final one, is the prefix Q. And this does the reverse of what P does. So it's pretty much the inverse of the prefix P. So here we have to find a value X given a particular probability. In other words, we'll be told that the probability of the random variable being lesser than or equal to some number is K, and we want to find X given K. So this is more specific, that find X given K such that the probability of X being lesser than or equal to some number small x is equal to K. And this is also applicable for discrete and continuous random variables, but we'll predominantly use it for continuous random variables. So these are the three big prefixes. So just remember what D, P, and Q stand for, and we are ready to begin the calculations. And once again, I encourage you to refer to my Excel videos, because some of the reasoning behind why we write down the formula in a specific way is much more detailed there. Here, I'll go over the basic calculations. Okay, so first, we're going to start off with binomial distributions. So we use binomial distributions to characterize events which have a success-failure type outcome. And the probability of success is given to us. And we are generally interested in understanding or calculating the probability of X successes in N trials, where the probability of success in each trial is given by P. So if you have, say, you're flipping 6 coins and head is defined as a success, I may be interested in a question of, what's the probability of finding 3 heads in 6 flips or 8 heads in 12 flips of a coin? Those can be answered using binomial distributions. So here we take an example of rolling a fair die, and we are interested in finding out the number of ones that are rolled in 6 rolls of the die. So if I look at the number of ones that I could potentially roll in 6 rolls of the die, the random variable could take on all of these values ranging from 0 to 6. And if I'm interested in asking the probability of rolling X ones in 6 rolls of the die, I am essentially describing something which could be very easily captured using the binomial distribution. Rolling a 1 is a success, not rolling a 1 is a failure. So I'm interested in how many ones I'm rolling. So I'm interested in how many successes I have in n trials. So let's begin. So what's the probability of rolling exactly 3 ones in 6 rolls of the die? So the word exact is our keyword here. So we are essentially looking to find out probability of x being equal to 3. And the prefix that is associated with giving us the exact probability is the prefix b. So we write down b followed by the name of the distribution. So we're just going to have a command saying b binom. See how it shows up here immediately. So binom, open brackets. The first argument is x. X is the number of successes we are looking for. Size is the number of trials we have, and we have about 6 rolls of the die. And prob stands for the probability of success, and we're going to do 1 by 6. And we can ignore the last argument that is not relevant for us. So this is our code. Now when I run the code, I get the answer 0.05358. And that is the probability of rolling exactly 3 ones. Let's go to the next one. We want to roll at most 2 ones in 6 rolls of the die. Now, at most 2 can be written down as x being lesser than or equal to 2. So this includes 2, it includes 1, it includes 0. So we're essentially trying to find the cumulative probability of this particular random variable. So for cumulative probability, we use the prefix p. So we have p binom. We are looking at the first argument here, q, stands for the particular number here at the end, which is 2. Size is the number of trials, which is 6. And probability is 1 over 6. And we're just going to do that, and we'll ignore the rest of the numbers, the rest of the arguments for now. And let's, okay. So there's an additional parenthesis which came in, now it's fine. And there we go. So the answer is 0.9377. Now the next one is a little bit different. What's the probability of rolling more than 4 ones in 6 rolls of the die? So we want to find p of x being greater than 4, and note that we do not include the value 4. So p of x being greater than 4, I can use the law of complements and say I can write this down as 1 minus probability of x being lesser than or equal to 4. So essentially, x being greater than 4 here would just count x is equal to 5 and x is equal to 6. Now, x can take on values ranging from 0 to 6. So if I only want to find the probability of 5 and probability of getting 6, I can also compute that as 1 minus the probability, the cumulative probability from 0 to 4. Because I know that the probability of all of these should add up to 1. So I use those principles, and I can rewrite my answer this way. So if I want to find the probability of rolling more than 4 ones in 6 rolls of the die, I'll write that down as 1 minus p binom, 4 successes in 6 trials with a 1 in 6 probability in each. And I'll do control enter, and my answer is 0.00066. Now let's do the next one. The probability of rolling at least 4 ones in 6 rolls. So this one is very similar to the previous one, but a little bit different. At least 4 ones means 4 is also counted. So I'm looking at x is equal to 4 plus x is equal to 5 plus x is equal to 6. So just by looking at things here, I want to find the probability of 4 plus 5 plus 6. And because I have a very neat cumulative distribution function that R offers me, if I can rewrite x being greater than or equal to 4 using a notation which had some lesser than or equal to probability, my life is going to be easy. Now, x being greater than or equal to 4 is all of these 3. So if I compute the cumulative probability of the first 4 numbers and subtract that from 1, then I'm on my way to finding the answer. And that is precisely what I will do. So this is just nothing but p of x, 1 minus p of x being lesser than or equal to 3. Notice that though these two questions, C and D, are very similar, There are subtle differences, and you have to pay attention to whether the question is asking for more than a particular value or at least a particular value. And that will define how we write down these complement statements. And you have to remember that you're looking at a discrete random variable. So now let's go ahead and write this down. So we have 1 minus p by norm, 3, 6, 1 by 6. And we have the answer 0.0087. And that is how you solve the first question. Now I'm going to do one more question here, and I'll leave the rest of it as an example figure. Now, the second example says, the probability that the San Jose Sharks will win any game is 0.3694 based on a 13-year win history. Now, winning or losing a game could be modeled using a binomial distribution. And we're told that an upcoming monthly schedule contains 12 games. So the first question says, what's the probability that the Sharks will win exactly 6 games in the upcoming month? So we are essentially looking for P of X being exactly equal to 6. So we are looking at 6 wins in 12 games. And we are given that the probability of winning a game is 0.3694. And because this number seems to come from historical records, we can assume that this probability of winning is constant in every single game. So what's the so we have our data here, right? So we have that the number of trials is going to be 12, which is 12 matches, and the probability of success is 0.3694. Now we're ready to solve the problem. So let me just move this line there, and let's begin to solve this. So because it's an exact probability, we use the letter D. So we have D of binom. We have 6 successes from 12 trials with the probability of success being equal to 3694. And the answer is 0.14763. And that's it. Let's do one more. What's the probability that the Sharks will win at least 5 games? So here we want to find P of X being greater than or equal to 5. Well, this is nothing but 1 minus P of X being lesser than or equal to 4. So once you subtract the cumulative probability of outcomes 4 and below, you're left with the probability of outcomes 5 and above, which is what we want. So here we just do 1 minus P by norm, 5, 12.3694. And the answer is, I think I have, oops, there's a mistake there. So this is 4. And the answer is 0.4733593. And so that's how you solve this using R. It's even quicker here than in Excel. And I encourage you to get comfortable and familiar with both versions. There's one more example question here, and I'll let you solve this, but I'll just put down the answer here. So the answer to this particular question is 0.171875. So go ahead and try that out. And I'll see you in the next video where we solve some, we find probabilities for the Poisson distributions. So I'll see you there.